Development Program on unveiling emergency trends in AI and data renaissance. It is my pleasure to introduce today's esteemed chief guest, Dr. Manu Madhavan sir, who is currently working as an assistant. His research interests span various domains, including bioinformatics, natural language processing, deep learning, graph neural networks, and machine learning. Regarding his honors and achievements, Manu Madhavan sir is recognized as a NPTEL star performer and has contributed significantly as a project intern at DRDO Bangalore. He holds a PhD in computer science and engineering from NIT and MTech in the same domain from Government Engineering College, Calicut. He has made remarkable contributions to journals, book chapters, and conference proceedings. He is an active professional member of the Association for Computing Machinery and lifetime member of BioClose, the Bioinformatics Association of India. He also serves as a reviewer for prestigious journals and conferences in the field of computational biology, bioinformatics, and applied computing. He has delivered inspiring talks and sessions on various topics related to his research areas. With over 6 years of teaching experience in various reputed educational institutions, he brings a wealth of knowledge and expertise to our session today. We are truly delighted and eager to hear from you, sir. Without further ado, I invite our chief guest, Dr. Manu Madhavan, sir, to take over the session. Thank you, sir.
Thank you for the introduction and a warm welcome. Thank you for this opportunity. I hope I
Thank you,
am
sir.
audible. Let me try to share the screen. So I hope my screen is visible. Could you please
Yes,
confirm?
sir. Your screen is visible, sir.
Yes, thank you. So as video is mandatory or shall I switch off? Yeah. So welcome to the session. As you already know, today's topic is basically an outline on overview of deep learning methods for natural language processing. So it's a vast area, like uh, what I can tell or what I cannot tell. It's very the scope is very high. So what I'm planning to do is give an overview of the evolution of deep learning models happening in NLP area. So my presentation will start with an overview of what is NLP. So you should understand what is NLP and what are the challenges involved in NLP. So we'll go through different phases happening in NLP, like morphological analysis, lexical analysis, kind of steps we'll discuss. Then we'll discuss about the challenges or happening, like what are the challenges, why NLP is so hard. That problem we'll discuss. Then we'll come into the concept called language model. The solution, overall solution is language models. Then we'll discuss about various language models, such as, say, we start with rule-based language models, then go for statistical language models. Then comes the neural language models, where this RNN, LSTM, all these terminologies will come. And finally, we are in the state of large language models. So we'll give a glimpse of what is basically this large language model, or what is the core part of LLMs. So that in that way we will discuss the evolution of NLP models or deep learning models for NLP applications. So that is the overall plan for this around 75 to 80 minutes talk. So let's start with this presentation. So this basically I compiled many images, references from many places. So I duly acknowledge all the contributors, even though it's not properly cited due to some business. So let's start with some intuitive examples to understand what is basically NLP. So Google searching may not be a not made, like it should not be a new term for you. All of are searching many things, and you can see the difference. If you observe closely, observe, you can see the difference happening in that field from an old search to the new search. Initially, the Google search engine is basically an information retrieval kind of model, which give the link for corresponding, or it maintains some indices, and using that based on the search query, the query keyword, we'll specify the term keywords. It's basically a keyword search engine. We'll provide the keywords, though we are searching something like who is president of India and all things. We'll get, the machine will take the keywords and make the search and give all the relevant documents. So the term is important, term is relevant documents which contain that keyword. That was the approach that maintained by the all search engines. But later you can see that when we are searching something, for example, you can search the query how old Obama. This is an old result screenshot. You can see that instead of giving all the documents which contain Obama or old or how, whatever the words, they give some results. You can see here that the answer is given here. Also something like Barack Obama or some descriptive box of Obama is also already also given. So the search from, initially I told use the term information retrieval. Now the terminology, it goes to information extraction. It's not give the documents, retrieve the documents which contain the information. Instead of that, this model, now the search engines are capable of retrieving the documents or extracting the necessary information based on the search query. That is one change you can see. And we may also use some kind of Google assistants or Alexa kind of things for many things. Voice based assistants, we'll give the voice comments, the system can understand the voice command and give the reply on text or something. Like instead of typing all the things, you can search for this here. Can you play music for kids? Or Alexa, can you play a melody song? Or what is the weather now? Is there any chance of raining today? So all these kind of questions you can ask, and Alexa will return reply based on the data processing, data base, or the access data access it have. They will give the information, not just the information. It will give the right extracted information. It's not just retrieving. So the main change you can understand from this slide is from information retrieval to extracting based on the query. It become more kind of conversational models, not just give a query based retrieval and a conversation based retrieval. You can see the difference. So more natural approaches are coming. Like you can ask queries in natural language. You are not bothering about the keywords. The system can understand the context. The system can understand the query meaning, the semantics, whatever it is required, and give the right answer with some precise information. And this figure you may be noticed in many cases is a figure from logs about parliament basically. In that you can see that when honorable MPs, member of parliament, they are using some kind of headsets when they are listening to the proceedings. So what they are doing with this headset, they are actually learning something, like they are listening the speech. So there is some kind of automated translation happen, like from it's not just a automated translation, voice translation. It's basically simultaneous real time interpretation system. So the parliament uses simultaneous interpretation system for instant translation of speech and its simultaneous delivery between many languages, almost all languages like Kannada, Hindi, Tamil. So it's a cross link, like Tamil to English, English to Hindi, Malayalam to, like all kind of cross translations. Speech level is happening when they are doing the speech in real time. I'm just introducing some application, then finally coming to what is common in all these things. That is my strategy. There is no surprise. And this tool you already know. We'll give some query in one language, and many cases the language can be automatically detected by the machine. That is another thing. So language detection, you can see here automatic speech recognition, speech translation, whatever, many things. Then English, it will automatically detect the language and translate into whatever language you want. Tamil you can select Tamil, Telugu you can take, Malayalam, Hindi, whatever languages you want, you can do the translation, and immediately this have some application like some OCR kind of application. In signboard, you may be in some other part of the country where you cannot find any English signboards, or all the signboards are in a regional language. So what to do to understand these things? You can do some scanning over the signboard, so it will detect the text in the content, maybe in different language. So this kind of APIs can detect the language from the OCR, from the image, and can be translated into any language. Suppose you are at Malayali or you are Tamilian, you can automatically translate into your native language. We can understand the sign. So here you can see translations, so cross-lingual applications, multilingual, especially in India, where we have multiple languages and multiple dialects of the same language. So in all these cases, this may be a good one. I cannot uh, continue without including this kind of example. So what I ask ChatGPT is the question: Can you create a code over NLP? So what I thought is beginning with a quote on natural language processing, like, or usually we'll start with some quotations by some famous people, so that we'll get a catch over the top. So for that purpose, I asked ChatGPT about a code for NLP. So they give the content like NLP waves the tapestry of human expression into the fabric of computation, bridging the chasm between words and understanding with the threads of algorithms and meaning. Wow. So out of curiosity, I want to give citation, because after doing PhD research work, everything, this is mandatory thing whenever you are writing some academic or research work, citation is required. So to add the citation, I asked, who told this? So the reply was very surprising, that I mean the ChatGPT, that generated the code myself based on your request for a code on NLP. So you should see how deliberately this good or how apt this definition, or how apt with the context of NLP, like it processes the weaves of tapestry of human expression into fabric of computation. How beautifully they use the language. That you have to note. And it is not attributed to any specific individual. If you are looking for a chords from notable, that's my mistake, I will not ask for chords from notable figures, like give me some notable chords from somebody on NLP, then it may retrieve the already available chords. But just I asked to create a chord, so I take the create in that sense and created a beautiful chords over NLP. So here you can see that the machine can generate wonderful quotes, wonderful text, even document, papers, thesis, whatever. There are a lot of things happening with this kind of generative models. And you may ask one question: how these all are possible? Or why I choose this example? What are the commonality in all these examples? You have many ready-made answers, like it's all about AI. We are in the age of data science. We have many things to do, like it's artificial intelligence product, or it use machine learning models, deep learning models, large language models, many keywords you can see, or computational intelligence, data processing, pattern, maybe the odd term, maybe pattern recognition, many statistical models, probability statistics, many things are there. So it's basically the product of all this combination, all this things. So yes, many advantages are because of this terminologies like AI, ML. They can do the great things, like driverless cans be there. It can beat the world champion in chess or any complex game. Many such patterns you can generate. It's possible. But how about an automated customer care? Like you are now contacting many automated chatbots for giving the like getting the results, inquiry results. So will it understand a baby's talk? So what I want to tell is, understanding human language is important in all the application that we discuss so far. So it should understand the context, it should understand the meaning, it should understand the natural, and it should generate the results in a natural way. So we are talking about Turing test. What Turing test say? It should understand that the this is not given like the person on there's a communication between machine and a human. So the communication should be so natural that the person on the other hand should not understand that the reply or the messages are coming from a machine. So that kind of naturality should come over the machine. So in all these cases, it should understand the human language, which is very important, which is very complex. So natural language processing, as ChatGPT given the definition, it's all about computing the language, or we can say how the language is processed by or understood by, or how to make computers understand our language. That is the questions. Any language, any natural language, not programming language. That's why we specifically saying natural language. Or how we can use the computational models, for example, graph or a parser or some kind of any like regular expressions, whatever it is, or how small or big it is, how we can use the computational models so that we can represent the natural language for the computer understanding, or the information represented in the text or natural language can be understood by the machine. Why this is important? Most of the information, like we are living in a data exploding amount of data, big data era, right? So and almost all data are what I can say, the source of data is text. They are text data, like WhatsApp messages or social media posts, newspaper headlines, newspaper newses in online on news in online platform, or whatever search query, SMS, text, whatever the data, the communication happen over the web. It's in the form of text. Images, videos are there, but most of them are in the form of text. So application of NLP as a crucial role in processing this information, because computer is living in a like the old age definition of computer, or old definition of computer was computer is a machine for processing data, raw data into information. Now we are working in above the information level. We need to extract the knowledge as well as apply this knowledge for a wisdom level. So that kind of applications are required. So the understanding of language is very important. For example, web search, advertisement, email, customer services, language translation, healthcare, many applications you can see. In all these things, natural language processing capability or understanding the language by machine is crucial. And there are, we can say this is a multidisciplinary area. It is not just about computer science or programming. As far as the computer science people, it's all about programming, modeling, deep learning, machine learning and all, but it is generally a multidisciplinary or interdisciplinary in nature, where the computer science involve programming, machine learning, algorithmic perspectives are there. It should have a linguistic approach, like how we can understand the linguistic phenomena. Once we understood the linguistic phenomena, we can apply the computational model. Statistics is involved, all about probabilities, many things are there, we'll come into that. Suppose we are working in some specific language, say Telugu or Malayalam, we should have expert in that language. And there are many socio-linguistic, psycho-linguistic impacts also there, like how the human process this things, like how the semantics of the word is coming, or how the context is settled by the persons. So many things are there. Social, like a word may have multiple meaning in multiple person, multiple areas. The same word may have a positive meaning in one place and have a negative meaning in the as a bad word in another part of the country. So multiple social, cultural, psychological, cognitive, many levels are there. So we'll focus on the computational aspects of this language processing. And where we are in the way to achieve many things, like many applications are coming with tremendous result. uh, it may start with a simple spell checker available in Word or any other text editor. Now a part of speech tagging is made for many languages are available. What part of speech tagging means, for those who not know, like suppose I have a sentence, the boy ate apple. So I will assign, the machine will assign a tag like POS, like this is a determinant, this is a noun, this is a verb in past tense, and this is a noun. Like that, it will assign the category. So that automatically it have to do. Why challenge means a word can have multiple senses. The same word can be applied in multiple senses. For example, bank. The word bank can be a noun as well as a verb. Like the banker, you can bang on. So the bank is used here as a verb. So in which category the word is used here, that is the problem. So how to understand that as a challenge. So many part of speech taggers are available. Why this is important? Because extracting the information, this kind of tagging is important. So the boy ate apple. What the boy ate? Suppose I ask the question, what the boy ate. So the boy will eat something coming after the eight, a noun that is coming after the eight. So the boy ate apple. So what will be replaced by this apple? Or who ate apple? So the boy ate apple. So I can understand who ate apple by we'll looking to the noun. And we can ask many questions to the verb. Like, so if we identify which is the verb, usually the verb will be the head of every sentence. Kriya, like it will be the most important thing. So we can ask many questions: who did, how did, when did, that kind of questions we can ask, and we can get the information. So identifying this POS category is very important. Or many most of the mail applications have a spam checker, spam detection. They are not automatically, like it's not detected by a person, like seeing in being sit behind your screen and checking all the mails mapped into this one. It's an automatic system that will identify what is the tag, what whether the mail is spam or not, based on the content, based on the source of the email. Many criteria are there. It automatically do the spam detection. Or email categorization, you can see that email have different category, like social, public, some kind of personal, private, primary, some kind of categories are there. So when a mail come to the mailbox, it automatically classify into the class. So mail categorization, machine translation, we already saw the things, information retrieval, sentiment analysis, chatbot. Now we can add something like generative text generation, then image caption generation, video subtitling, many applications you can see. But at least this kind of things we have achieved almost a good percentage of accuracy. Now the other things are coming in the list. We can add many applications. Almost all application now have some NLP component, whatever be the things, like whether it is a software optimization, whether it is a operating system level working, theory level working. What we are trying to do is convert it into some kind of NLP problem, then solved by the LLM models. That is, like, even it's a biological problem, computational biology or bioinformatics problem. Everything is now boils down to a LLM kind of language modeling problem. So the application, the way we are going is very fast, very quick. Along with this one, we can in parallel or in as a synonymous, we can say there is a word called computational linguistics. So computational linguistics provided an automated solution for NLP problems. So this we can say two sided, like one is NLP, which focus more on the application part, where the theoretical foundation or the computational models that can be used for the linguistic application. So basically they work on the theoretical part on the of the linguistic. So they are called computational linguistics. So earlier there was a debate like which is whether computational linguistics or NLP is good, because NLP people may are more practical. They are focusing on the application, where computational linguistics, they are linguists. They check the linguistic theory and try to use the computational model to represent the linguistic theory. For example, you have a spelling like why this is different, like quickly, and I couldn't get that example. Why the next, like always q follows the next word, usually follow you. Why q always follow you, not other things? So can we model this kind of things? Or can we use a finite state automata, DFA or NFA, to represent the morphology of a language? For example, how boy plus s forms the plural form boys. So how we can automate this kind of morphological results using some computational models? That was the main intention. So linguistically component computers who greatly facilitate our interaction with machines and software. So this is one another perspective where we focus more on the linguistics perspective. But nowadays, the barrier, the gap between computational linguistics and NLP is very small. They are merely used as a synonymous word. For example, how y ly in ally and quickly are different. So both are ly structurally similar, but they are different. Or we can say the sentence, tell me what is the difference between water the flower and drink the water. We can understand there is a difference, water the flower and drink the water. So in water the flower, water is basically a verb. We need to water the flower, so water is a verb. But drink the water, here verb is used, like water is used as a noun. So how we can understand this difference, like even though they are similar in surface form, in the spelling they are same, but there are difference. Their role, functional role in the sentence by the word water is different. So how we can understand this kind of things is a question. Or I ate idli with chutney and I ate idli with brother. Structurally both sentences are same, idli with chutney, idli with brother, but the meaning is different. I ate idli with brother and I ate idli with chutney, the structure is different, you can understand. Or how you can convert something into Sugamano. Like there are three words in English, how are you, but in one word in Malayalam, or kaise hai, aap kaise hai, some kind of translation. So how we can explain these things, or how we can understand the phenomena happening in this kind of differences. That is basically computational linguistics follow. So understanding NLP, CL will help a better. So what is the goal of NLP? Basically to form a natural human to computer communication. We should go a long way, but still we are on the right way, we feel, based on the progress is happening. We are on the right way, we are reaching closing our ultimate goal. But more practical goals are, like more practical applications, some amount of error may be there, like Google translation you can see many errors, but still they are useful in for at least they can give a platform to start something. No need to start from the scratch. So more practical and more deploying in this they are. So more engineering goals, we are focusing more on the engineering goals. Through multiple engineering goals, fine tuning the engineering goals, we can reach the ultimate goal. That is the overall idea of what is NLP. And why NLP, we already saw. This is data driven application. We have a lot of applications, social media posts, Wikipedia articles, many things are there. And mining this data for useful application is essential. So NLP deals with developing application, process, and understand this textual data automatically. So for any query, or we'll take the query at the end. Yeah. So what we discussed is intuitive idea of what is natural language processing. Now, when it comes to the theoretical idea, there are different levels of language processing that start with phonology, morphology, lexical analysis, syntactic analysis, semantic analysis, discourse, and pragmatic. This is coming from the linguistic background, but it is applicable to computational linguistics or NLP also. So phonology basically deals with the sounds. So how we can identify the basic phonemes, we'll call. So they are called phonemes. The basic unit here is phonemes. So how to understand the phonemes, or how different phonemes come together to a sound. Different sounds come together a phonemes, or how these phonemes form a word. How for a given a speech sequence, how we can identify the words from the sequence. What are the words? How we can understand the poses. So all these are the phonology level question. I'm not focusing more on the phonology. I'm not an expert in. So it involved many speech signal processing and all. So we'll skip this part. But this is phonology. We'll focus on morphology. Once we have a speech and we convert it to some kind of text. So how we can break down the words into its morphemes. How to identify the structure of a word. For example, boy is there. So how boy plural form boys is formed. We are adding boy plus one suffix, so it become boys. There are two types of way to generate this kind of things. One is inflection, like boy plus s boys, play plus s ploys. We can apply some rules. The other one is derivation, like we have one, say compute is a verb. We can convert this compute into computational. So computational become an adjective. So this kind of Morphology is called derivational morphology. Inflectional morphology is some kind of just adding like boy plus s boys. We'll get the same category. Like boy is a noun, its inflected form is also a noun. Or play is a verb, playing is also a verb. So this kind of morphology is called inflectional morphology, while derivational morphology will change the category, POS category, for verb to noun. For example, Google is a noun, so Googling is a verb. So using this kind of morphology, we can generate new words and new usages. So morphological analysis will tries to understand or break down the word into the corresponding morphemes, or which part of the morpheme or how the morphemes join together to form the word. That is the main question, morphological analysis. The next level is lexical analysis. Once we identify the morphemes or morphology of the word, so here we first need to identify the tokens. So how we will define the tokens? How we will define the words? How we will assign the meaning to the word? So boy is a word which is a singular word. It's a noun. Its meaning is this one. Its category is this one. So all this kind of properties we can assign at lexical level. So lexical level mainly identification of individual words and the corresponding meaning. Now comes the syntax, where we need to grammatically arrange the words, sequence of words. So a text is basically sequence of words or sequence of character. So how we can use the grammar, like I should always form am, I am going to. So if it is am, the verb should be in the ing form. So that kind of rules are there. So how we can use or teach the model to follow the grammar. Then semantic level we'll discuss with the word meaning, like a word can have multiple meaning. Like the bank can be a financial bank, it can be a river bank. So how to identify which is the right meaning in the sentence, in the context. So it will helps to arrange the identify the disambiguate the words from the sentence. So once a sentence is processed, we'll go to the next level where discourse analysis. So how to make connection between the sentences. For example, I have a sentence. Uh, uh, there may be different things. No smoking areas. Hello, hookah, not but cigar. Okay. Suppose I have a sentence. There is sorry, I will write it again. There should be no space. No smoking areas. Hello, cigar, but hookah. This is my sentence. So it can be interpreted in many ways. Like no smoking area, hello, cigar. So one interpretation can be in some way no smoking areas are there, which allow cigar but not hookah. Or you can also interpret it as that no smoking area, like in some hotels and all, smoking areas are there. So none of the smoking areas allow cigar, but hookah may be allowed there. So two meanings are there. So how to understand the right meaning of the sentence? We need a context. So some previous sentences may be required to understand what is the right interpretation of this sentence. So that is basically discourse analysis do, how to connect the different sentences. Or I will say I watched Transformer, which is a good movie, or it is a movie. Like I watched Transformer, it is a good movie. So to understand what is Transformer, or I read Transformer. I read about Transformer, maybe. It is a good movie. So this Transformer word may have multiple meaning. It can be LLM transformer. It can be from the electrical transformer. So many transformers are there. So you read about transformers. It's a good movie. So based on this context only, I can understand that this transformer is about movie transformer, not about LLM or any other scientific transformer. So this is basically the discourse analysis do how to give the references. So this it refers to this movie transformer. And pragmatism is all about the contextual and common sense. For example, I can ask that two sentences like, can dog swim? Can dog swim? And the same question, can you close the door? So for the question, can dog swim? The answer will be something like yes or no. But when it comes to the question, can you close the door? It is basically a request to close the door, not asking the ability to close the door. Can you close the door? Yes, I can. And if you are sitting there, that doesn't means the response is not that expected. It's actually expecting you to as a request to close the door. Okay, so that kind of understanding require a common sense, world knowledge. So pragmatism is all about how the contextual and situational meaning can be used to understand the sentence. So all is basically how to understand the language and then how to generate the language. For generating as well as understanding, we should understand the structure of the language. So in different level, we can understand from morphology, lexical, syntax, semantic, discourse, and pragmatic level, we can understand and we can use this kind of analysis to understand. And based on the understanding, we can generate the sentence. So why the NLP is challenging? One thing is it's all about the context sensitive. Like when we are communicating, we have a common context, and based on the context, on the background of this context, we are talking. If this context is not there, we cannot understand each other. So human communication involve many forms of signals. Even we can use silence to communicate many things based on the context. So that is very important. And understanding this intent of the communication is very challenging. And ambiguity is everywhere, even lexical level, structural levels, index level, semantics level, all levels you can find the challenges. For example, lexical level, you can see rows to put rows on her rows of roses, many rows. So they are hyponym, like similar in pronunciation but different in meaning. This rose may be a name, this rose may be a verb. So many things are there that is not easy to understand. Or he saw a sawmill. So saw is a word. This two saws have, one is verb, one is noun. So that is the lexical level ambiguity. On the other hand, structural level, say the professor said on Monday he would give an exam. So there are two interpretations are possible, two structures are possible. Say the professor say on Monday that he said on Monday that he will conduct an exam on some other day. Or we can also interpret on some other day, say maybe in Friday he told on Monday he will conduct an exam. That is also possible. So two interpretations are possible. The boy saw a man with telescope, many things are there. And when it comes to idioms and phrases, it become more challenging. You can see one idiom like kick the bucket. So basically the term kick bucket indicate the event of death. So the all girl finally kicked the bucket. When I translated, I'm not sure how many of you can understand Malayalam, but you can see this one, Hindi and Tamil at least. I not included Telugu or any other language. So this you can see the difference. All will take the direct meaning of this words, like kick the bucket, like they directly converted this bucket into the corresponding term bucket, not take the meaning of the phrase kick the bucket. None of the translation tried this one. So coming with that kind of analysis is very challenging, that making NLP very, we'll say it's very hot here. So the hot depends on the context. Here hot may be some 32 or 32, above 32 degree may be hot, but in some other places, very cold places, even 20 degree may be hot. So it's not quantifiable. It's very imprecise and vague. It depends very much on the or it vary person to person. Like I already mentioned this example, can the dog swim, which expect an answer yes or no. On the other hand, the same structure, but it's a question, is a request, not a question about the ability. And many things are non-categorical in nature, so the meaning of the word is non, we cannot fix like a classifier, we cannot always give one meaning, we cannot assign, we cannot map a word into a meaning, or a meaning and word cannot be mapped. It basically depends on the sentence. Meaning and usages are changing time to time. For example, while in the earlier use it was meaning of time, like take a while, but now we are using as a subordinate clause, like something happened while he was playing, the accident happened while he was playing, or the person came while he was playing. So while was used as a subordinate clause, so the usages are changing. And same way to have a multiple part of speech, like a so, and the so was sharp, so the same word can have multiple things, and there was a gradual change in usages also. The meaning gets changed, new words are coming, and all these are issues in the NLP when we are doing some research work in. All these are basically open problem we have to solve in complete perspective in many languages. So basically, we can say two approaches. Now we are coming to the this is an introduction to NLP. Now we are coming to the core part of the or the other part of the things, like deep learning part, not directly deep learning. We talked about many issues. We talked about many applications. So the question is how to solve these issues. So there are two applications or two approaches. One, we have some grammar system for most many of the languages, not most of the languages. Many well like when defined languages have like highly resourced languages like English, Chinese, French, even Indian language, most of the languages, they have a well written rules, grammar. So we can teach, or we can represent these grammars in some machine readable form using programming logic, like a logic programming, or some kind of functional programming, or kind of at least some if else rules. We can write these rules, or some DFA kind of things, regular expression, DFA, finite transducers, all these kind of methods you can use. You can use all these things to represent the rules so that it can be represented. So all the grammars that we can use, all the linguistic rules we can represent using the computer logic, and some exceptions may be there that also will we will define by the rule. So that is one approach, that is rule based approach. Another one is ask the machine to learn from the data. What we have is a plenty of data. So can we use the machine learning capability or statistical learning capability to learn from the data? So rule based approach is very good, very precise, because it have a definitive rule, and it will cover all the, like all the cases which covered by this rule will be well understood by the machine. But it is less scalable. It is suitable only for a closed domain. For example, earlier NLP applications, most of the application technology, computer related applications are over the defense systems to make the almost all technologies are evolved around the defense department. They want to make their defense system more advanced one. So NLP was one part of that, trying to convert the messages, secret messages, or some kind of commands given by one language into some some kind of English to French, or French to Greek, some kind of translations. They in that domain, the words are very limited. The word meaning are less ambiguous. For example, if you are taking one domain, say defense domain, each word have a well-defined meaning, or a legal domain. You can take a domain. In that domain, all the words have a clear meaning, a one meaning, a unique meaning. So in that case, a rule based approach will be very effective for a small domain, closed domain, where the where we have a small size of vocabulary, and each vocabulary have a definitive meaning. Then that is okay, we can go for a rule based approach, which will give a zen percentage or 100% clear answer. But the problem is, for a general purpose domain like news domain, or more large corpuses where each word may have multiple meaning. In natural language, we can say that is not scalable. We cannot scale the rules because there are more exceptions than regular things. So all these exceptions cannot be captured by rules, and which rule to be used, that then there will be some ambiguity. So all this will lead to a complex system which will fail. So for a large domain, this is not scalable and this is not practical. So a rule-based system is not a recommended one. Earlier models of the NLP, or even especially for Indian languages, they are probably mostly on rule-based systems. For example, translation, rule-based translations, purely dictionary-based. We have a database of word and the corresponding meaning. We'll do some kind of rules and we'll try some rules and do the translation. So that was the earlier machines which are not practical. Then the other approach is empirical approach, which is more practical. What we can do is we can learn from the data. So in this context, what they are doing is we have a large collection of data. They want to learn the pattern. So instead of saying that this is the rule or this POS tag should follow the other one, we'll take the probability. We'll learn how many times the noun follows a determinant. So previous word is determinant, then how many times it follows noun, how many times verb follows a determinant. You can see that normally a noun follows a determinant, not a verb. So this is most probable case, this is the wrong case. So the system can learn from the probability distribution or the statistical distribution of the data instead of teaching that this should be the rule. So that is empirical approach. So when we are talking about the approaches, we should talk about uh, the idea of language models. So what basically a language model do? We can say that language model tries to understand the linguistic phenomena in very simple terms. So it will model the language. So what do we mean by modeling the language? More simple terms, we can say that, for example, I have a sentence: the boy ate dash. So given this sentence, the boy ate dash, what will be your prediction for this term? So definitely you will say something like the boy ate apple, the boy ate orange, or the boy ate mango, boy ate food, boy ate Italy, boy ate something. So usually say something edible things. You will not say the boy ate a mountain, the boy ate a car, the boy ate something. So boy ate a book. You will not tell, right? So you can understand that some words have a affinity in this context. Given the word ate, some words are more preferable than some other words. So words have some affinity with some other words. So if we know this affinity or this probability distribution, this is basically a probability distribution. What we are doing is we are computing what is the most probable word here given the context the boy ate. Given the context the boy ate, what could be the next word? Or generally we can say what will be the probability of the word WN given the previous 1 to n minus 1 words. So given this n minus 1 words, what could be the most probable word here? So what we are computing is the probability of the next word in the vocabulary given some set of previous words. So that is basically a language model, or we can say it will assign the probability of a sequence of words. That is also possible. If you know this probability, I can compute the probability of the sentence, the boy ate apple. So what is the probability of the as the first word? So I will use first word using the simple into probability of boy as the next word given the previous word is the into probability of ate as the next word given previous word is words are the boy into probability of say apple given the boy ate as the previous word. So what is this probability? That is what actually they are trying to compute. So language model in short tries to compute the probability of the next word given a previous set of words, or compute the probability of the entire sentence. So we can, out of this all the probability, we can choose the best probable word. If you are generating something, you are given some prompt, like you are given the word the. So what could be the most probable word for the next place? It can be boy. Then the boy, given this boy, what could be the next word? Then given the boy ate, what could be the next word? So in that way, it will generate the content. So some context may be given to generate something. So it's basically compute this probability. Now, how to compute this probability is the next question. Do we need to capture all the previous history? It's not easy, right? So I will take a new page. Suppose your sentence is the boy ate apple. So the boy ate apple. You are computing something like probability of say apple given the boy ate. So what is this probability? You can easily compute this as count of the boy ate apple divided by count of the boy ate, right? Probability of A given B is probability of A intersection B divided by probability of B. The same rule we applied here. This is what we are computing. So suppose these three words, the statistic, we are searching this count from a corpus. Suppose this number, this kind of pattern, this exact patterns is very less. For example, the boy ate apple only appears one time out of, like, we have say some 100 words which say the boy ate, and only one time the boy ate apple comes. So what will be this probability? 1 by 100. If it is very large, like 1000 or million, it becomes 1 by million. So it becomes 0.0000, some small value, or even 0 is also possible. If it is not appearing for a long sequence, what I'm trying to say is, for a long sequence, getting the sufficient statistics will be very difficult. So it may lead to a zero probability, and it may cancel out all the computation. So to avoid that problem, one, and in many cases this kind of long dependency is also not required. Like the next word apple majorly depends on 8, because the previous word is 8, the next word is apple. So only some limited amount of previous history is required. So they are appearing the concept called Markov model. So Markov models, what basically do is, it will compute this probability. So for example, probability of Wn given previous n minus 1 word. The first order Markov model say that this is basically Wn given Wn minus 1. It just depends on the previous word. We assume that this is Markov assumption. We assume that it just depends only on the previous word, not on any other word. So this probability can be approximated by just counting this probability of n. So this easily we can compute. So this is called a bigram probability. We'll call it as bigram. Or in some cases, we can also write as WN as independent of some previous word. In that case, we will call this probability, we will call a unigram probability. Bigram, similar to bigram, we can think about diagram, and generally we can say it just depends only the previous n words. So we'll call an n-gram probability. So instead of going for the entire sequence, entire previous sequence, it will maintain a n-gram probability. So n-grams are important. So n-gram may be bigram, trigram, that depends on what model we are using. So instead of picking the words and the whole previous history, n-gram model will choose the probability, compute the probability of n-grams. So this probability will be available as a dictionary, as a database. Using the database, we will pick the most probable answer. So that is one important aspect. So initial model was rule-based model. We are talking about the evolution of language models now. So the first application was purely rule-based, but rule-based applications have some limitation which is not scalable. It's a very limited application over a closed domain. So we are not recommending rule-based for a general domain. Then what we think about is a statistical model or empirical results. So first model what we discussed is basically n-gram model. So we can, instead of going for the whole statistic, we talk about n-gram models. That is one application. So many statistical learning models are there, like they use Bayesian theorem, naive Bayes algorithm based bias approach is there, Markov approach, hidden Markov models. HMM based applications. So many statistical models are there. The basic idea is they compute the probability of the pattern. Then learning these important features and all these relations become very complex. And at the same time, the evolution of deep learning models over the other domain, like especially in image processing area, image processing, and all other structured data combination like feed forward neural networks, CNN. All this brings to the idea of neural language models. Neural language model. So in all these cases, you should remember that what a language model means. A language model tries to read this probability. So given a text data, a sequence of words, it has to learn the probability of the next word in the sequence or assign a probability to a sequence of words. So neural language models evolved, which tries to mimic the same thing, like instead of doing this prediction from a statistical perspective, n-gram probability or something, it will tries to get the representation, get the result from using a feed forward neural network or a CNN. So they try to feed the words to a feed forward neural network. It passes to many layers, hidden layers, and finally predict an output or the next most probable word as the output. So that is what happened in neural language models, which where the deep learning applications become more prominent. But when it comes to a feed forward neural network or this kind of CNN, there are many issues, okay, which is not suitable for NLP problem. So what a feed forward neural network do? It's basically expect a structured data. For example, you have say a patient ID and results of T1, 3 clinical tests, and finally the disease status, yes or no. So P1 some values and yes or no. P2 some values 3. So for this kind of P100, all these values will be there, and you have some idea yes or no. So you will design a neural feed forward neural network with 3 input, then many hidden layers, and finally the output that will predict yes or no. So this is a feed forward neural network. For even image, you can take an image of fixed size, say 28 cross 28 or 2 to 255 or 2 to whatever. We'll take a grid of image pixels, and a fixed size image will be fed to a CNN model, and it will process and do the classification of whatever be the task. So in all these cases, you can see that the input size is always fixed, which is not suitable, which is not correct with respect to language data. We cannot say the language, the sentence will always have 5 words, or sentence will always have a word, even word also will have always have a 5 character or 6 character. That is not possible. So these models are not suitable for NLP because they are always expecting a fixed size input, which is not guaranteed in NLP. The second case, uh, not all problem can be converted into a fixed length. We already saw each input of the network was independent to the like. Next thing is, when we say a feed forward neural network or a general machine learning, it will say that the features are independent. The input data is also independent. Like in the previous case, we have patient 1 and patient 2. So we can say patient 1 and patient 2 are independent, right? Or image 1 and image 2, they are independent. But this is not true for sentences or sequence of words. They are dependent. Like the next word depends on the previous word. So that dependency is also very important. So many application input depends on previous data. So these are the two issues. For example, I want to generate the word deep. So D is the first letter. Based on that, it will generate E. Based on E, the next word will be generated. So this way, auto completion problem you can take. Given a word, you need to complete the sentence. So it depends on the previous inputs. So that uh, we cannot skip. And the length of the input also not constant. It may be 4 word, 5 word, 6 word, 7 word, whatever be the number, it depends. Number of characters may depends, so we cannot fix it. So this is generally called a sequence learning problem, and we need to look into the sequence dependence. And what we are actually ideally wish is we need to look into the sequence. The dependency should be captured between the words, and it should be like length invariant, like number of the inputs equal, number of the length of the input is not it should not depending on the number of the size, input size. And at each time we are doing the same operation. At each time step basically we are doing the same time. Like first time step we are doing taking D, second time step we are generating E, second third time step we are generating P, like that. In each time step we are doing the same operation, take the previous input and generate the next output. So this is required, and there are many applications like next word generation, predicting the POS, predicting the sentiment of the movie, text, any text, speech, videos, time series, many applications you can see. So how do we model such tasks involving sequence is the question. So what is our requirement list? It should account for the dependency between the input, because CNN, FNN cannot be used for this task. It should be variable length. Again, CNN, FNN is not possible. And each time step we are using the same task. So in CNN, this kind of concept is not there. Time step concept is not there. So what we can do is a new architecture which support all this criteria is called RNN, which is the most prominent NLP, or at least we'll say currently the NLP is before transformer and after transformer. This we have to define and treat NLP in different way. Now I am talking about the before transformer era, so BT we can call. So recurrent network was the neural network was the prominent. RNN in short was the connection. So what RNN do is, as you can see, there is one input layer that will take a word at time, or whatever be the input, character or word. Then it will pass to the hidden layer and give the output. So basically we can say Xi is the input. This is the input layer, and this is the hidden layer, or one more output is required. This is the output. So yi is the output. So this will generate an hi. So let's take this u as the input parameter weight, and we sorry, this is u and this is v. Here parameters are not required. So this is input layer. Between input and hidden layer, this is output layer. We have a parameter u and v. So we'll first compute the hidden unit hi, which is a function of u xi plus b. So b is the bias. We'll ignore the bias first. So u xi, u is the parameter, and yi is, we'll take this hidden output of the hidden unit. Some activation function there is there. So all are basically the neural network. I hope you already have some idea of how the neural network is working. So f is this one function of v into hi plus c. So first thing that we are doing is we are using the same network in each time step, and we'll share this parameter u and v, whatever be the parameter. So parameter sharing ensure that it is independent of the length. Whatever be the length, we are using the same parameter at that number of times. Suppose I have 10 words, I will use the same network 10 times. Suppose I have only 5 words, we'll use the same network for 5 times. So at each time step, we are just making multiple copies of the same network. That is one change we are going to do over normal network. Now another condition is that it should depend on the sequence. The previous connection should be like previous input, it should depend on the previous input. So how we can do this dependency? One approach we can say y1 is a function of x1, then y2 will take the previous two words, y will take the like not previous word, current word and the previous word. So current word and the previous words. But the problem here is that it is not true, because we need one more thing, that at each time step it should repeat the same operation. So time step 1, this is the function f of x1. Y2, the time step 2, this is a different function which take two arguments. Y3, it will take three arguments. So in each time step it is basically performing a different task. So how we can account this dependency is the question. That is the most beautiful part of a recurrent neural network, because each time step it is the problem. So solution is a recurrent connection. So we'll consider that we have the model, like this is the input layer, this is the hidden layer, and this is the output layer. So what our current architecture is, this u and this is V. This is hidden layer. This is time step t minus 1 you can take, and we are at the current time step t. So we are using the same model, we are copying the same thing, same parameters, everything is same. So only difference is that, so this is xt, input is xt, here you can take the input xt minus 1. The only difference is that we are using a connection here which is basically w. So we are using ht minus 1. So we can write the equation. So initially ht, that is hidden state of the tth time step, is basically a function of xt, that is the tth input, this one, comma ht minus 1, that is the hidden state of the previous one. So ht minus 1 in turn depends on ht minus 2, and which depends on ht minus 3. Like all the dependencies are there, h1, h2, h0 till h0, all dependency will be carried at this time. And yt will be, that is output at the t time step, will be f of ht comma ht, like it's basically yeah, we'll write it as ht is u xt plus w ht minus 1 plus some bias b, and yt is v ht, so this will be used here, plus bias c. So this will be the solution, the recurrent connection. So what we are doing is we are adding one recurrent connection, this one, which make the dependency correct. So this, so what each time step we are using the same function. So this is what we are doing, and each time step this hidden state we will call a state of the so instead of hidden network we are using the term state. So at each time step we are calculating the we are using the previous state the state in the previous time step, so that the recurrent connection is possible. So this is what basically an RNN. So this RNN will compute the probability. So this can capture the sequence dependency and using the sequences representation. So output of this, the final, suppose we have this word. So this output of this one will be basically the representation of the language from x1 to xt. So output of us, we can take at each level, we can take the output, or we can take the final output, which will be the representation of the, suppose my word have 5 words, my sentence have 5 words. So output of the fifth time step will be the representation of entire sentence. So this is one way a neural network, a recurrent neural network is used to capture the sentence representation. So this is the basic idea. So there are many types of RNN connections are there. One is one to one, like each time step we will take the output, or some kind of image captioning, like it will take one image and multiple output, so one to many. So input will be an image, then it will go through the RNN connection and many, so it will generate one to many RNN, or many to one, like a sentiment analysis. It will take a text document, that is a sentence, as an input and predict one at the output. Or it can be many to many, like a translation application, like will both input and output will be multiple RNN. And what we are doing here is, this is the architecture, like basically this is the architecture. We'll use some activate linear combination. It's very similar to any other neural network, only difference is that we are using this recurrent connection, and the hidden function probably will be in the tan h function. And finally what we require is a probability distribution. The language model expect a probability of the next word, so we'll use yt, the softmax function, which give the probability distribution value between 0 to 1 as an output. So output layer we will use a softmax function to get the value. And training, we need to do the training. This is basically a probability distribution, so we'll do the cross entropy loss. So output, suppose my vocabulary contain 10 words, output will have 10 nodes, each will give a probability value. and this is basically the distribution, probability distribution. Suppose I have 10 word, suppose my next word to be predicted is word 1, so the original distribution is 1 followed by all other values 0. So here also we are expecting that the first word will have a higher probability and all other have a small probability. So this will be a probability distribution, and then we are comparing this to probability distribution. So to compare the loss between two probability distribution, the loss function that we can use here is cross entropy loss. This is equation. So then we'll this is single the total loss will be the sum of individual loss, and we'll do the differentiation gradient descent operation with respect to the parameter. Here three parameters we define: u between the input and hidden unit, v between the hidden unit and output, and w between the hidden state. So all these parameters should be learned accordingly. And the training is basically the back propagation. We can do it for the output layer, it is easy, but for the hidden layer W it is very difficult, because suppose you are in the fourth time step, this L4 depend on the state 4 and state 3. The state 3 depends on state 2, state 2 depends on state 1, state 0. So all these dependencies have to be maintained when we are computing this L4. So a normal backpropagation method cannot be applied here. So what we are doing is a backpropagation through time. So I'm not going to the details. Basically what we are doing is there are two part, one explicit part that depends on the current state, and we take the sum of all other part in the previous state. So it's a recurrent connection. So this is the key part in any RNN models, the backpropagation through time. Because of this previous state dependency, we cannot go for a normal backpropagation. So we have to backpropagate through the time to capture this value. Some dynamic programming methods may be used to fasten this kind of training. So far we discussed about the prominent model called RNN. After RNN, we got many RNN family algorithms like LSTM, GRU, by GRU, and many things. But basic problem with RNN is that one is exploding gradient and vanishing gradient. So we should understand what this problem means. Because the RNN models depending on the previous words. For example, I am in the 100th time step. I am using the recurrent connection which use state 99 for the 100th time step, T900, which this 99 actually capture the information from 98. 98 capture 97, like S0 till S0 to S99. All the informations are carried here. Because of this extra information, there is a high chance that this value becomes explode or vanish, the gradient. So explode in the, suppose the value here, accumulated value is very small. For example, you can say some zero point 0.1 or something. Each time we are doing some kind of multiplication, so some kind of exponential analysis. So 0.1 raised to some t. So at t times step we are doing this operation, so we'll get a very small value like 0, 0, 0, close to 0. So in that case, the gradient value is very small, and the backpropagation algorithm update the weight as wt minus 1 plus this gradient, some learning rate into this gradient, right? So since this value is very small, the entire things will go 0 and there is no weight update. So the gradient will not progress, it will stay at the same position. On the other hand, suppose this value is very high. Suppose this is some kind of 1 or 2. 2 you take, and it repeat the 2 for or 2 some large value for some t time step. So we'll get a large number, and this way we'll get a large value for the gradient, and this gradient cannot be used, so we cannot reach the local maxima. It's a convex optimization problem. It will get a very it will take a long step to finally get the local, so we may not reach the problem, and we need to memorize all the things. So memorization is a problem. Then the next word, like next work in the RNN family, uses algorithm called LSTM. So RNN should remember the flow, the statistical model, then the neural language model, FF and CNN, they have some issues, then proposed RNN. RNN has some issues, then proposed LSTM model. So we'll quickly go through LSTM also. So this is a problem. So this is a problem. The clouds are in the sky. So the sky actually depends. Suppose the next word is sky. The sky basically depends on clouds, right? Only this information is required, not the previous all previous information. So the dependency of this weight, the next word with the previous word is varying, not immediately previous word. Only some words are important. So how to capture this word importance? Word answer to this sky. The word do not any further context to predict the last word in the above sentence. Like I have seen in Spain for at least 10 years, I can speak fluent. So Spanish. So since the word Spain is here, this is important to predict the next word. So this depends on many, not all the previous words. So this issues was there. So approaches is truncated backpropagation and get LSTM is the solution that we are going to discuss. So the what we can do is we can take a whiteboard analogy. Like we have a fixed size whiteboard. If we are writing continuously over the whiteboard, it come full and it become information overloaded. We cannot get the right information at right time. In order to process the information, we may take a lot of time. So what we can do is we can selectively remove some of the content which are not usable. We'll keep some of the information which are required and we'll use that information for the next step. So we may skip few steps, selectively write. We may skip some previous step, that is selectively read, and some of the information which are absolute we'll delete them so that the memory size can be controlled. This idea is called a long short memory idea. So we are applying some kind of filters to get this idea. So let us assume that we are at the time step t minus 1, and while doing the teeth computation, we'll do the selective read, write, and forget. So what do we mean by selective read and write? So what we are doing is we have st. So we are not keeping the whole information. This is the original equation, like st minus 1 plus uxt. So instead of keeping all this like all this st minus completely, we will introduce a parameter ot minus 1, and only the selectively forget item or selectively written item will be kept to the next thing. So RNN will learn ot minus 1, a vector that will say how much of the previous information to be required, like ot minus 1. So we are computing ht minus 1. This ht minus 1, instead of directly computing this ht minus 1, we will first compute an ot minus 1, and based on this ot minus 1, we'll just apply the ot minus 1 over the original ht minus 1. Suppose I'll say simple word, like I have some values, say 10 values are there, 0 0.8, 0 0.2, 0 0.3, 3 values I can take. Then this is ht minus 1. Suppose I know that this is less important and these are more important. So what I can do is the ot minus 1 will say the previous step may be some high importance, this may be less important, this may be less important. So instead of keeping the entire value, we will multiply it with ot minus 1. This ot minus 1, this weight we cannot give directly. We have to learn from the other parameters. So during training, we'll add one more parameter ot minus 1 to selectively write the content from the previous step. Similarly, we can do the selective read as well as selective forget. And after these three things, we'll get the final st, which will give given to st minus 1. So you can see that instead of directly going, we are applying the gates ot, it, and ft. Ot stands for the writing, selectively write, selectively read, and selectively forget. So st is the one, like sigma of this one plus uxtb. Then we'll do the st and all the steps. Like I'm not going to the details. We have only 10 minutes. Yeah. So we then there comes many applications, like we'll say RNN family of application algorithm scheme, RNN. So recurrent neural network based LSTMs, like LSTM and its variants, like LSTM use one LSTM used for like bidirectional LSTMs. Then similar to LSTM, there is also another concept called GRU, then by GRU, by RNN. Many such different algorithms are came with many applications. Some algorithms tries to add linguistic features, like LSTM already use some filters or some gates. Along with the gates, can we introduce some more information? For example, the grammatical relation, the dependency between the elements, can we use? So they tries to give more input, more information to make the LSTM or RNN algorithms better. That was the results. Then came encoder decoder models, like one encoder and one decoder are there. Like encoder will do, for example, I have a translation application. I have an encoder. So this encoder will take the text and give a representation. This representation will be used by another model decoder that will decode and give the output. So encoder may be an LSTM or any another RNN, and decoder will also be an RNN that will take this input and give the output. So then so many issues, like for example, I can say the boy ate apple, or the boy went to school. That, and you can try the corresponding translation. Some ladka school jata hai I'm not correct. Some boy going to school, you can take going to school. So ladka school jata hai, jata hai, something you will get. So when you are when say ladka school jata hai. So when you are translating the second word school, it actually, here it is fourth word or fifth word. The school is basically like to school is coming in the different order. So when you are translating this word, we have to focus on this way. So encoder models, the word order in the source and target may be different order. So in order to make that focus correctly, they introduce the concept called attention. I'm just quickly going the concept. So encoder model, then comes the attention model. All the idea is still language model. They are using the language model concept to like predict the next word or predict the probability of the sentence. They use different language model applications of RNN. Like they even tries to combine RNN and CNN to get the better results. So CNN has some capability of convolution operation to make the representation more clear. So they take the advantage of that representation to along with the LSTM, which can capture the recurrent connection. Some RCNN's models are there. So LSTM CNN model, many combinations were tried till 2017 when the paper, the transformer was published. So when this kind of RNN family getting prominent over NLP applications, there was a thought process that still the models, the RNN families are not efficient, at least as far as the computational facilities are concerned. For example, we have a lot of high performance computing facility, but still that cannot be utilized over LSTM or RNN model because they are working word by word. If you remember the procedure, at each time step, the LSTM model will take a word at a time, or word at a time. Since it just working on the word at word level because of the recurrent connection, because ST depends on ST minus 1. So without processing ST minus 1, we cannot work on ST. So that dependency is there, which cannot be, so that we cannot work in parallel. We cannot use the distributed computing or some parallel processing capacity to work over LSTM. And because of this recurrent connection for a long text, this process become very slow also, because it cannot be run and lot of parameters, lot of complex data procedure. So training procedure is very complex. We cannot work in problem. But when we check the architecture, we can see that the input to the most of the model is word embedding. I not covered what is word embedding. Word embedding is just a representation of a text. We'll represent the word as a vector. So word to vector we can say. So normally the word vector coming from a general corpus, not from the pre-trained model, not from the input text. And all the word embedding is already available as an input at the beginning step itself. Still, we cannot use the word embedding. We cannot use this model. Like we cannot use the encoder, at least encoder process in parallel. So, and the word ordering is not important because we are focusing on attention. Attention mechanism order is not important. Still, all these properties are there. We cannot do the parallel processing because of this recurrent connection. So we require a new architecture which can do all this kind of things, which will use attention and parallel processing. That is the architecture called transformers. So transformers is a deep learning model that adopts the mechanism of self-attention and differently weighting the significance of each part of the input. It allows parallel processing in the encoder part, and it do the bidirectionality. It have attention mechanism. Because of this attention, the word ordering is not important. It can process in parallel, and this representation can be used by the decoder model to get the more get the relevant probability distribution as the output. So a transformer is basically a language model. More precisely, it's an encoder decoder architecture, but it enables a parallel encoder computation so that the representation learning will be more faster compared to RNN or LSTM model. So this is the architecture. You can see it will start with an input, then word embedding as well as a position embedding will be there. The position as well as the word will be encoded. That will be given to the encoder module. There is basically a stack of encoders are there. This is one block. There are such 6 or 7, 8, that depends on the architecture. Block will be there. Similarly, this is the decoder block. We'll have some 6 to 8 n number of decoder blocks will be there, and each encoder block follows a attention mechanism. This is called a self attention mechanism. So the attention score, the importance of word with respect to the other word in the context, will be captured by referring the same sentence. So it will refer the same sentence for an input sentence and read this attention score, learn this attention score, so that how important the word with respect to, or what are the other words with respect to the words in the other kind. For example, I will give one example. Say the cow cannot cross the road. It was too tired. The cow cannot cross the road. It was too congested. So two sentences, we have the same structure. So when the transformer or when the model processes the sentence, you should understand that what this it refers in the sentence. So you can see that in this sentence, the it refers to the cow, and in this sentence, it refers to the road. How we can understand this? Because it was too tired, so road cannot be tired, only animal can be tired, so cow, it refers to cow. Here we can say too congested, animal cannot be congested, only road can be congested. So this difference can be captured only through self-attention. So self-attention will say what word should be focused when we are processing it. So it, rod will have more importance than cow in the second sentence. Cow will have more importance, more weight compared to rod in the the first sentence. So this will be understood by a self-attention. That is, each word with respect to the other words in the sentence will capture a context vector. So that context vector will be used to learn the relationship between the word. So a multi-headed attention will be like multiple attention will be heads will be there to capture this importance. Then a feed-forward neural network can will normalize the weight, and finally the encoded input will be given to the decoder. Decoder also have a masked attention, a similar concept. Then a cross attention between the encoder and decoder, one attention is there, as we discussed in the encoder decoder model. And finally a feed-forward neural net that will give the vector. Then finally the output layer, we are expecting a probability distribution, so we have softmax at the output. And this architecture is the key component in today's LLM. They are used in different ways. One is the encoder only model. Encoder only model in the sense they just use the encoder part of the transformer. For example, BERT and its variants, Albert, Robert, all other BERT family, they use this encoder property. So given the text, given the bidirectionality, all these things, the transformer model, they can give a representation of the text. So this representation, the encoding, can be used for the other downstream task. Some models like GPT, they use the decoder only transformer. They use this decoder property which generate the text. So they have the capacity to generate the text. So they focus more on the generative part of the transformer, that is the decoder part of the chat. So the current LLMs are the this two part. One is BERT, which focus more on the representation, learning the representation of the data. So again, it's a language model, but over a large language model. So over a large amount of text, they learn the data. Then this part, GPT kind of things, they use the learned part to generate the text. So they are focusing more on generating the data. They trained over generating data. So what LLM do is, that is the current new trend. Instead of specifically design a deep learning model for a particular task, for example, LSTM model for text classification, LSTM model for translation, LSTM model for sentiment analysis. So in each time we have to learn, train the model for sentiment analysis task. Then we will train the model for another task. So in each case, we are training the data for a specific task, model for a specific task. So instead of that, a large language model learn over a large data of various tasks. So this language model can be used for multiple tasks. So we do the pre-training over a large corpus. Then this will be fine-tuned for a specific task. That is what basically a large language model tries to achieve. So this is the current trend. What we discussed is a journey from the beginning to the current trend in the NLP. We started with what is NLP. Then we move through the different the applications, some intuitive examples. Then we discuss what is language model. Language modeling is the key solution for almost all problems in the NLP. So how aptly it model the language. So the idea is that if it can predict the next word properly, that understand the previous context is correctly understood. So that is the key importance of large language models. So we tried different method. We discussed different methods, evolution of language models, starting from a rule-based, statistical, n-gram models, then deep learning models, RNN-based recurrent models, then the transformer models. This is the evolution. Currently, we are in the stage of LLM that us what we are enjoying the GPTs and BERT models. So this is the overall summary of the presentation. I hope you got an idea of the evolution. So if you have any doubt, we can discuss or over to the organizers.
So,
Yes.
welcome participants. If anyone have queries, let's discuss with sir.
Sir, good
Yes,
evening, sir.
please. Good evening.
Yeah, thank you for such a detailed presentation on NLP.
Thank you.
Yeah, sir. Actually, can you please discuss some of the recent, recent research topics in NLP?
Yeah.
Some problem areas where we can focus our research on.
Yes, understand. So currently, the NLP area is very very challenging because we have a large language model which change the complete picture of the NLP research. So one way is so you when we are trying with NLP works, definitely you should try for LLM kind of application. Otherwise, you cannot compare the results with, if you are still trying with deep learning models or LSTM models, you may not able to compare the results with LLM. So one is you can try for LLM like core architecture of LLM. Any LLM model you can try. So can we explain the working of LLM? So explainability over the LLM models. We can link it into the fairness, ethical issues, many things are there. So how we can use or assure the fairness of LLM models, because that is a challenging problem, because how the language model learn or represent the the general content. For example, one issue not reported was that a large language models trained over some data, they represent say always represent a doctor as a male and nurse as a female. So that representation is wrong because we have female doctors and male nurses. So the model is very biased actually. Because the data is biased, the model is also biased. So how to work with that model bias? For that we need some fairness treatment, or some kind of interpretation over the model is required. So that is one area where we can explain the models, LLM models. Second case is the current trend is RAG, retrieved augmented generation. So ChatGPT, they are generating some hallucinated contents. So instead of that, the idea is, can we add some more facts so that the generation could be more fact oriented? So retrieval augmented generation is another area where you can explore the LLM, or you can take a domain and tries to fine tune the LLM models. For example, a legal domain, how we can use the LLM so that we can use the capability of LLMs to explain the legal documents. So that many of the legal content cannot be read by a naive person. So can we use the LLM ability to give a more readable content of legal domains, or any educational domain you can try. So domain specific adaptation of LLMs is another area, or you can work on local languages where the resources are very less. So LLM for Indian language is or how to redefine the LLMs in Hindi context, which can capture all the diversity of this language. We cannot dilute the language diversity for the sake of technology. We should capture the language diversity along with this recent technology. So we need to augment the models for Indian context. That is another area. Explainability I already mentioned. So working principle of LLM is still like what they are learning, each layer of the encoder, what they are learning is still not clear. Can we tries to compress the model? So currently the it is not accessible to everyone. LLMs are still with like only big giant companies are producing LLM. So even in an academic setup, it is very difficult to train an LLM model. Even Google Pro also not supporting. We need the sufficient hardware resources to do all this kind of training. So we cannot come up with our own LLM. We have no this kind of support. So can we tries to do some compression without affecting the quality? Can we whether all these parameters are required? Can we do some parameter compression over the LLM to get a better results? That way, many options are there.
Yeah,
Thank you
thank
so
you,
much,
sir.
sir. Now I would like to invite Dr. Hemalata ma'am for vote of thanks.
Thank you, ma'am. This is my immense gratitude to deliver the vote of thanks. I would like to extend heartfelt thanks to Dr. Manu Madhavan, our distinguished guest and assistant professor from IIT Kottayam. Sir, your insightful and enlightening presentation has added a significant dimension to our understanding of NLP, computational linguistics, levels of language processing, challenges, evaluation of the language models, with a detailed explanation. We are truly privileged to have benefited from your vast knowledge, sir. Once again, thank you, sir, Manu Madhavan, sir, for enlightening us with the details of NLP, which given more information for research scholars who want to do research in NLP. So this is a memorable and intellectually enriching experience for us, sir. Thanks, sir.
Thank you all the organizers, participants for the opportunity and patient listening. So thank you all. Good night. Thank you.
Thank you so much, sir, for the wonderful presentation.
Sir, can we close the session? Can we close the session or are we getting any feedback link?
దగ్గర ముగ్గులు కురుస్తున్నావా? இது போட்டுருக்காங்க ஃபீட்பேக்.
ஃபீட்பேக்கா? ஃபீட்பேக் இதுக்கப்புறம் தான் லிங்க் அனுப்புறோம்னு நினைக்கிறேன்.
டைப் பண்ண போறீங்களா?
ஆமா சார்.
Feedback link is already shared in the group, I think.
The feedback group already share பண்ணிட்டாங்க.
It's already there in the WhatsApp group.
Yes, ma'am. Yes, ma'am. We'll go through it. Thank you, ma'am.
Thank you, sir. It was a very good session.
Thank you. From our end, we have enjoyed this session. Thank you. Thank you so much.